Yeah. Okay. Okay. I'm sorry. I have to upload in the first one, but I can't upload. You have at least on my. That one, configurating one. That one.
Yeah, but it's
Okay.
Hello, it's working. Hello everyone, welcome to the kernel testing and dependability micro conference. So just to get started, so we have some people attending online with big blue button. Feel free to leave any questions on the chat there. Unlike last time, there's no people attending live on the video on big blue button, but if you leave a question, we'll forward them to the speakers. And thank you to our sponsors as well, of course. And so we have a pretty packed schedule, so I won't talk for too long now. We have Veronica and Mark talking about integrating testing with maintainers' workflows. So if you want to come here, and then I'll pass the mic on to you. Of course, we have. If you have a question, raise your hand. We'll give you a throwable microphone as well.
So hi, I'm Veronica. I'm the tech lead for CK project. We're doing continuous integration for kernel testing, both for Red Hat and for various upstream trees.
And I'm Mark Brown. I do kernel stuff, and occasionally that involves dabbling in testing. So the goal of this session is that we should want to have a discussion about how we can get maintainer and testing, or maintainer workflows and testing workflows joined up with each other, because at the minute it's not ideal the way that's working. So we've got a few slides prepared here, but the goal is that that the slides will not take very long, and then we'll spend the rest of the time discussing. But even with our slides, feel free to sort of interrupt whenever you feel like. So if I can work out how to advance the page with this. Nope, that goes full screen.
You're supposed to do that. There's the button for the slides on the bottom.
Oh yeah, so there is, yeah. Computers, who can, I don't know. So the problem space is basically we have a lot of people working on developing the kernel, obviously, and we also have a lot of people who are working on testing the kernel in various capacities. So some of that is that we have people working on writing tests, either as part of developing something, they need to make sure that the thing they developed works, they wrote a test, or it's just a separate effort where somebody's decided that they'd like to improve kernel quality and they just want to write some tests. They go ahead and do that independently of any active development. And in addition to people writing the tests, we also have people who sit down and run the tests. And obviously, a lot of the time, the people writing the tests will also run their tests. But there's also a community of people like Veronica who mainly run the tests, or mainly take existing tests and run them in an effort to monitor the quality of things they're releasing, or in an effort to try and help upstream development. And often these two groups don't really work together very well or at all. They don't communicate very much. And that's unfortunate. So what we'd like to do is talk about ways in which we can get the developers and the testers communicating with each other. So the testers are testing things that the developers care about, and the people doing the development are providing the testers with the tools and information they need to verify that what's being shipped actually works in a useful fashion. And that's fine. Okay, so there's varying levels of success with us at the minute. Some places things are working really quite well. So, for example, K-self-test is really heavily used by some of the kernel subsystems that use it at all. And it's also something that's been picked up by quite a lot of the testing systems. There's some rough edges in places, but it's an area where everybody's joined up with each other. Similarly, for the graphics test suite, IGT, I think that has an expansion that isn't Intel Graphics Test anymore, but I can't remember what it is. That's something where QA people know that it exists, developers actively use it, everything works great. V4L compliance, same story. It's a requirement to get stuff into the kernel, but it's also something that testers are aware of, and they're picking it up and using it. However, there's some other issues where it's a bit less joined up. So XFS tests is heavily used by the file system developers, and some testing people use it, but a lot of the testing efforts just don't run it at all for a bunch of reasons. One of the big issues with running XFS tests is that it's quite demanding of the hardware it runs on. So actually deploying it will. The cache box isn't on. That's on.
This one's on. Try it.
Test. Oh, testing works. Thank you. This is an excellent test suite. No, XFS test doesn't have particularly high demands of the hardware it runs on. I run it on my laptop all the time. What it does have is significant, you need significant expertise to set it up. And you need significant expertise to interpret the results.
It depends on what hardware you're looking at. It can eat SD cards and things like there's no tomorrow.
Oh, okay, so, yeah, that's fair. I mean, I run it on my laptop on a KVM, and I think, you know, if I can run it on my laptop for a couple of hours, you know, anyone should be able to. But I mean, you're quite right. If you run it on real hardware, it will absolutely chew through an SD card.
Yeah, that was what I was thinking when I said demanding. Yeah, in terms of actually running it, like it's yeah, interpretation can be an issue, but yeah, in terms of it's not that it needs a high-end system. It's just that it can. Some systems are very low-end or not very durable, and obviously it hammers I/O for obvious reasons.
But the other thing I'll mention is that there are various people who have set up different turnkey setups for XFS tests. You know, Louise has KDevOps.
Yep.
I have my KVM XFS test, GCE XFS test, Android XFS tests that, you know, all run from a single test appliance. But they all generally tend to have fairly strong assumptions about your runtime environment because of the interaction with storage. And so it's not that bad, but you know, if you have your own test environment that you've already optimized other tests for, the turnkey systems that either Louise or I have set up might not necessarily work with your infrastructure, and that's a problem.
Yeah, and knowing what to do for your infrastructure and how to solve the problems for it. I mean, yeah, Kent Overstreet has something that runs XFS tests as well.
Yeah, and yeah. I know Joseph does for ButterFS. I mean, a number of us have actually developed our own homegrown test runners.
Yeah, so and this is
Yeah.
one of the areas where it would be good to have a discussion, I think, about how we share the knowledge about how you set up an environment to usefully run these things. I mean, audio is in a similar position. Next thing on the slide, where it's to test it, you often need some. Ted, you often need or some physical wiring of your system, which isn't necessarily immediately obvious and easy.
Yeah, to me, how to wrap XFS tests to just get test output in a standard format, that's a solved problem. The next thing that I'm looking at and wanting to talk to more people about is how do we get a common test format that works for XFS tests and everything else so we can get everything into the same CI. And I've heard of some talk about there being a CI that just ingests things in different formats. I think it would be a lot saner in the long term if we can just get things to output in a common format from the start.
So I'm not super familiar with XFS tests, but don't we already have KTAB for that? Like that's the format at least the K-self-test uses for outputting test results. Is there any reason that XFS test would use something different?
So XFS test uses the JUnit XML format, which is a superset in terms of the information you can express in KTAB. It would not be hard to write a Python script that took JUnit XML and like spit it out into KTAB. The reason why the XFS test folks probably aren't all that interested in switching to KTAB is JUnit actually is much more expressive, has a lot more information that we want. But if the idea is just to simply, ingest it into a common CI, that's actually, again, not hard. It's a Python script, and it's not a hard Python script.
Could you give some examples? The question was, can you give some examples? And you're just going to have to pass these. Yeah, Ted can't answer you without the catch box.
Anyway, yeah. Sorry, what was
Could you give us some examples of what you can express with and I take it JUnit is for expressing test results?
Yes.
Yeah. What can you express with that?
In addition to pass, fail, we get skipped, and we can also get a quick summary of what the failure actually was. And although I don't actually use it, JUnit also has the capability of putting like the D message or the system, the actual test output failure that makes it much easier for people to interpret what the hell actually happened other than it failed, right? Because this is the other thing that would be really useful is if you're going to have other people run tests for you, and then you want the developers to do something with it.
You want to collect as much
Yeah, one of two things needs to happen. Either it has to be trivially easy to reproduce the failure, not rerun the test, reproduce the failure, those two are subtly different.
Ideally not you.
Yeah, or
Do that.
all of the test artifacts, D message, the output from the test script, as much detail as possible, right? And again, those of us who are developers who do this, I have a tar.xz file that has all of the test artifacts. It's uploaded into Google Cloud Storage, and I can share it with other developers who I want to ask them about when I want to ask them for help, because I have all of the test artifacts, right? And that's something that, as a developer, is incredibly useful.
What we really want for that is just a directory that tests can dump, like core files. We want to make sure that if there's a core file being left behind, that gets recorded as a kind of test failure.
Yeah, and if and some way of telling the people running the tests what information it's likely to be useful for them to collect and share, because it's not necessarily
Just collect it all. Storage is cheap.
well, the idea of what is all, do you can go overkill and end up sharing so much stuff that the developers go, I can't even find what I'm looking for in here. Depending on what you're doing, some things are more focused than others.
I think if you just have a directory for results per subtest, has to be down to the subtest level, then
Yeah,
That's all we need.
which is something on the test, on the person writing the test side is to work out what to collect.
Then we have to plumb that through to the test, but the
Yeah.
starting point is like,
Yeah,
if not tapped, then JUnit, and we need something to start targeting.
So doesn't Linaro test string already do some of that stuff when if you go into Linaro, LKTP test site, they collect a lot of information. That would be a good one to look at. I think they gather DMSH as well.
And it's not necessarily the test author, it's the test running environment.
That's what I'm talking
Right?
about.
Yeah,
That's
so,
what I'm
for
talking about
example, you don't need to tell the test author how to save dmessage, right? It's the test running infrastructure.
Yeah. So what I mean is the person writing the tests, it can be useful to say a D-message would be useful here, or here are the the test author said, like for Ulster, we have a script that you can run on your machine that will go and grovel around in all the user space exposed to bug interfaces and dump everything out, so that when somebody wants to send us a bug report or a test failure, we can say to them, just collect this, and it will tell us everything we need to know.
Yeah, I mean, so again, this is in my test infrastructure, right, is I can actually pass in a set of shell script fragments that get executed at various hook points. So I can set up trace points, collect the trace points, and then, yes, it's dumped into the test artifact file. And again, it's not hard, it's just everybody builds their own system that is like purposed for them. And I think part of the problem is, you need to fund someone who is going to actually do something that's more general. Otherwise, what ends up happening is each kernel developer does something that works pretty well for them. I've actually tried to go out of my way to actually add documentation and try to get other people to use it. But again, I'm doing it in my own spare time, right? If I actually had someone helping me to improve the test running infrastructure, it would go a lot farther than a single developer who is only going to optimize his particular workflow, right? So
let me talk a bit about where this is going, what the dream is. If we can get one common output format that every test, everything on this list outputs to, and we can run them all from the same CI, then the next step is to get something like get maintainers, but for tests, where we can query for every CNH file that we changed, what tests need to run.
That's exactly the point that I had there at the end.
Yep.
Like it's really hard to even figure out what test subsystems are running, what test maintainers are running. It's not documented anywhere around the kernel, and get maintainers or some other similar file is actually a really good area where to share this. So this is also twofold. It's not only for the CI systems or test runners. It's also for the developers who try to contribute to the files or kernel in general. And as newbies, they might not understand really what tests to run when they are submitting their patches. So having a location that shares what tests are being run, what tests the sub-maintainers rely on, and what you should try to run yourself before submitting your patch to not waste everybody's time. Having all of this documented would be a good first step. What you're saying about the shared format for everything, that's a really great dream to have, but it's very far probably from the reality with the amount of different kinds of tests that people have. So we need to start somewhere.
Yeah, you also have to talk about what the goal is, though, so we know how to direct our efforts.
So can I just interject here and say that I think one of the big challenges is that many of the subsystems have bootstrapped their own test frameworks, like even inside of K-self-test. So like RCU torture is totally its own thing. And so just wanted to say that in my talk, I'm actually going to be specifically talking about that part of it. Like,
how do we wrap all those?
Yeah, like do we want to structure test suites to follow a standard configuration so that you as a maintainer can express how your test should be run to CI systems, so that you don't have to like go into every kernel CI and patchwork and everything and be like, this is how you run BPF and that's how you run RCU.
Yeah, that would be really nice to have.
What I think we could do, I'm not there yet in my own stuff, but this is what I've been working towards, is a test should be just a program that returns results on standard output in some standard format so that we can parse out subtests, success failure, and so on and so on.
That is K-self-test.
But can can you treat XFS test as a K-self-test?
Probably, yeah. This case self-test, sorry, I'll tell you later.
Yeah.
Okay, so RCU test is one of the ones that hasn't been really ported over to K-self-test. So it does, that's one exception under the directory if you look at it. But rest of the tests under K-self-test, they all run. You can run them with one command and they generate KDAB output, and then you can look at that. So that's there. So some tests on the slide that I have seen, there is a V4L compliance. And then also, I think, Ted, the XFS tests, we talked about it when we started K-self-test, and some of them, we decided that they are better off as on their own, especially V4L compliance, because of the dependency on some of the libraries and graphics. So XFS might not fit that model, but we have left out some things. It's a conscious choice. Maybe it's something that it's time for us to revisit.
Yeah, I think part of it is also about dependencies. So for example, for XFS tests, there's a lot of setup that you do once, and then you run a whole suite of tests. And that's much more efficient than redoing that setup before and after, the 500 odd tests that are in XFS tests. XFS tests also requires a lot of, DM setup, LVM. There are a lot of tools, user space tools that you have to have installed that a typical tester might not necessarily have installed on their system.
And you also have so XFS test is one of the ones that can run for quite a long time, for example. So you have different resource requirements for running the test, and testers need to know what they're getting into when they start running the test.
Yeah, so, and again, I think
have control over it.
Yeah, and again, it depends on what you're doing, right?
Yeah.
So what I tell my developers after they make a really, really stupid mistake is download this repo, read the KVM XFS test quick tests, and run KVM XFS test smoke before you send me a patch. It will take half an hour to run, right? Now, what I do is I actually run 12 different configs in the full auto setup. Each of those configs takes about 2.5 to maybe 4 hours if you're running on XFS. That's fine. I've sharded it to 12 different VMs in Google Cloud, and I get the results back in 2.5 hours. And I do that before I send the pull request to Linus. But not everybody needs to do that, right? I do that before I send the pull request, but that's not what I ask individuals to run, right? And that's going to be true for, I think, many of these sort of test infrastructures is there's what do you want the end users to run? There's what does the maintainer run before they send to Linus? And then you actually have what some of the really perfectionist QA people might want to run, which is looking for flaky tests, which, as Louise has pointed out, sometimes there are individual XFS tests that fail 1 in 200 or 1 in 800 tries. So he will actually run each test hundreds of times looking for the flaky test failures. I don't do that before I push to Linus. Other people do, right? And again, what is considered the right amount to run? And there is significant disagreement between the people who use it. So even if I wrote down, gospel according to Ted, this is what you should, I think you should do, there'll be 12 different people who will disagree with me.
I think we actually can and should standardize a lot of that stuff. My dream is, and what I've actually got implemented for my own stuff, is we want a CI that we can point to the Git branch. I've got a Git log view of test results. So results are all indexed by SHA-1. So before I pull someone's code,
I have that as well.
amazing. Let's get it all. Let's get all our tests pulling in, ingesting into something like that, and then we can have a common set of tests that anyone is expected to have run, and it runs on just at that point. Getting a cluster to run that stuff is a small ask if we've got the tooling in place.
So just a question. How many maintainers have actually declared what tests they want submitters to run?
Yeah, like the V4L people do. Some of it varies by. I maintain things with or drivers, and I can't. Even if I ask people to run tests, they could just lie to me. I have no way of verifying anything.
But do you like have a list somewhere? Hey, before you send a patch, please at least run these tests.
For some things, other things, it's difficult to test because of the way they plumb into the system.
If we get test results indexed by SHA-1 with the git log view, then we don't have to trust people. We can just look, are your results in the database?
We have to trust whoever puts stuff in the database.
Not if
Like
we just
everybody
have-
should run some kind of testing before they submit something. It's just like getting the
So
there
you
be that
are
assumption.
absolutely right that there is no good information for people. So we went and did some documentation a little while ago who went to use what between K-self-test and K-unit. I think it's a great idea to have a document under the testing docs dev process, having which test to run for when you touch a subsystem. We think it's self-explanatory because K-self-test does have directories named after subsystems, but having a clear documentation, you're absolutely right that we need that.
Yeah, this works great for self-test, but there was LTP mentioned, XFS test. There are other subsystems that might not have self-test or K-unit, but the maintainer of that subsystem most likely still runs some set of scripts or at least something before submitting the pull request.
So one idea that we were thinking about was, what if we added a new entry to the maintainers file so that under each subsystem you have a, please run these tests before you send me a patch. You know, here is just, you know, path to a script to run or path to a document describing the tests.
I've also got to jump back and push back on something. Documentation should not be required to run tests. Tests should be fully self-contained, and our K-self-test tests are not there yet. You have to dig around to figure out, I know at least for tracing, what are the config options that have to be enabled for these tests to run, and that takes a while.
How do you make the scripts, how do you make the test scripts work on all different distributions if they have dependencies on different kinds of hardware?
There's a config file.
Sometimes you just need a lot of things documented because it's not really easy to automate it across all the different environments that are supported on Linux.
Even for file system tests, right? We shouldn't particularly need special hardware. I'm thinking of some cases where, for example, there's a library function in the page cache that 4 file systems use.
Yeah.
How on earth do we say, if you've changed that function, you need to run this test with one of these 4 file systems? I mean,
right, that was my question, is like, oh, what tests am I interested in? Well, I just redefined memcopy, so all of them, like, but
well, I mean, you know what you're doing, and really somebody who is less skilled than you probably shouldn't be touching memcopy.
but I still want the test to run.
Yeah.
Let's not let perfect be the enemy of good. Let's at least get a mapping for every C and H file. These are tests that should be run when this changes.
Yeah,
What about providing, I don't know, some sort of a KVM image with all these tests preloaded, and all you need to do is load your own kernel into it?
So I really hate to interrupt the discussion, but we still have 1 point and we have like 3 minutes to get it through. So I would really like to just get that done, and then we can continue the discussion maybe in the hallway track if people want to. So we talked about how to figure out what tests to run. We mentioned that actually getting the test to run might be a problem, but another problem that we do have is interpreting the test failures. The test might fail because of infrastructure issues. The failures might not even be 100% reproducible, so bisecting the failures is very unreliable. There can be also, for example, a patch that exposes a failure, so the test starts failing, but that patch that will be pointed to with the bisection is not the cause of the failure, so you can get a lot of false reports just by trying to bisect the failures. I tried to talk to people on the automated testing call last week, asking about what people are doing before reporting the failures from the CI system upstream, and everybody said there needs to be a kernel person who understands that subsystem to look into the first failures, and that's what we've been doing too. The issue is that how do you make this scalable? How do you make this kind of working automated? The people who usually run the tests, we had that as a separate category in the previous slide, they are usually not experts on every subsystem. So we really do need involvement from the developers and maintainers to help triage the failures when they first occur, because they know what got merged, they understand the patches that were pushed to the gate. And if they see the failure, and since the tests we are trying to run, they need to be something the maintainers rely on. They should be able to like point fairly closely to what could have potentially caused the failure of the test. So that's the other problem that we have, and which we would like to hopefully find some involvement from people to solve.
Thank you very much. Next we have David.
No, that was last time. We knew there will be also a talk.
Yes.
Yeah.
Thank you. Will it refresh the page, or do you have to? Oh, enhancing case self-test. Yes. Thank you. And then full screen is.
Yeah, the three buttons or this one.
No.
The three dots.
All right. Hi, everybody. Thanks for coming to my talk. My name is David. I'm an engineer at Meta on the Linux kernel team. So the name of the talk is Checking Your Work, Linux Kernel Testing in CI, but I actually really want to discuss K-self-test more than CI. I'm sure we'll talk about that too, given the last talk. Before I do, can I just get a quick show of hands of who is like intimately familiar with K-self-test and understands what is involved with building a K-self-test suite? Okay, so I'll go over it in some detail. This is the basic agenda. I think the really interesting discussion is going to be starting at 2 when we talk about like fundamentally what is K-self-test, what do we want out of the framework. Feel free to interrupt me. I would just ask, it might be nice to get through like the mechanics of what K-self-test is before we have too much discussion, but it's fine. Feel free to interrupt at any time. Okay, so let's start with what is K-self-test. So fundamentally, in my opinion, it's a flexible testing framework for validating the kernel. It's flexible because really, I think at the end of the day, K-self-test is basically a way that lets you write user space programs that validate kernel functions, or not kernel functions, but kernel behavior, and then outputs it in KTAB format as we discussed. This is where it's located. Many different subsystems are tested. All use them slightly differently, some very differently, like RCU torture, as you mentioned. This is an example of a makefile in a K-self-test suite. This is really all you actually need to define a K-self-test suite. If you see here, you have test progs, which are instances of executable files that don't need to be compiled, but are instances of test cases. And then test gen progs are makefile targets that are compiled when the test suite is built that do need to be built in order to be run. So this is all you need. This is the C group kselftest makefile. Yeah, and these are the two. So this is an instance of the live patch one. These are all shell scripts. The live patch self-test suite relies on modules to be inserted. Live patches are actually just special instances of kernel modules. So those aren't really encoded in the self-test suite, but those are required in order for this test to have semantic meaning. And then RCU torture, like we mentioned, is just a make target that runs a test suite that was basically built by Paul McKenney and is specific to RCU torture. So they're all slightly different. They all have kind of different semantics and different requirements. And that's something that I want to discuss while we go through the presentation. Another thing I want to mention is that case self-tests can be built, installed, and run, meaning that you can specify a list of self-tests that you want to build, and then case self-tests will provide you semantics for packaging those tests together, spitting out a test runner that can run the test cases that are part of those test suites, and then you can run those yourself. I know this is tiny, don't have to worry about the specifics, but basically you install it this way. Case self-test outputs this directory here, which is the install directory, which has a runner and the list of targets that you wanted to run for your test suite, and then you can run it by executing the runner, and the runner just walks over all the test cases and executes them. Another thing I want to mention is that you can specify requisite kconfig options in kselftest. And one of the things I want to discuss is that this is really more of a convention, I would say. So for kselftest, you can advertise, I need these config options to run. Like for example, for live patch, you need config live patch, you need config dynamic debug, and the modules for the test live patch. But this isn't really part of the build system for kselftest. It's really more just a signal to somebody that wants to run the test. This is how you run them. And so with all that in mind, I want to take a step back and look at kselftest and consider what do we want out of this test runner and this test framework, and can it be extended to provide more value to people? So it was actually originally designed for ad hoc usage. The first commit that added it said it was basically just a place for people to dump test cases that were bit rotting on some maintainer server. Let's put them in a specific, in one place that's in the tree so that they can actually sit there and be useful to people. And the only requirement was that you had to put a run test make target in the makefile, and you had to add that to a root makefile in the self-test directory. And basically, the contract was to do this, and we'll run it for you when you run this make target. There wasn't really any imposition of structure on what these tests would do. I don't think there was even an imposition on like the output. I think KTAP came quite a bit later. And that philosophy is no longer true in the sense that kselftest has evolved. Now you do output tests. Test output is done in KTAP format. There's some expectation that tests will tell you if they've passed, failed, or skipped in a certain way. You can specify test cases in the makefile as opposed to just a single target that's a opaque thing for what it does, and they can be packaged and installed. But there isn't a common expectation for configuration. And one thing that I've noticed, at least when I was using kselftest, is you often, despite the fact that there is a common way to build the test and run the test, you still kind of have to be a little bit of an expert in certain subsystems, at least, to be able to know how to run it. For example, I don't know, many test suites don't use test progs. It's probably not true, because I know that RCU torture doesn't. But
So
yeah.
RCU torture is not actually. RCU torture, I would not use RCU torture as one of the examples because it's not even in the make file. If you look at the default targets, RCU torture does not show up in the targets.
Okay.
It does not, and RCU torture was never intended to be part of, actually included in kselftest. It doesn't run. If you run kselftest by default, RCU torture does not run. So it needed to be ported, and we haven't actually done that. So that has to happen before RCU torture can be run using K-self-test.
So that's a fair point. There are other test suites, I would argue, that are I think more canonical K-self-test suites that do a little bit of their own scaffolding, like at least BPF, for example.
BPF is another exception example, partly because it needs emulation. I mean, it's so, that's a little bit different.
So, okay, agreed on that. So
It's also not part of default, by the way.
Well, that is true, but I think one of the things I would argue is that a lot of these tests actually could benefit from some of the same infrastructure that something like BPF or RC Torture would. So, for example, sorry.
That is absolutely true.
Yeah.
What I'm saying is this is just been one of those things that has to happen. BPF is slightly different. It also has a dependency on Clang, another LLVM and Clang. So for that reason, if we were to include that in default, it can be included in the default. It just runs if you were to have the right things installed. However, we're not including it in default for a reason, because a lot of the environment like EMU, virtual environments, people want to just use very minimal set of tools. So you have to have a lot of tools to be able to run. And if you do have them, you can configure it to not run.
So I think I would, go ahead, Guillaume. No, 10 minutes. 10 minutes, okay. So I think I agree with you. I think I would say that the issue of missing dependencies or all these things are, at least from what I've seen, pretty common. And I wouldn't use the word ubiquitous, but I've seen it in a lot of the test suites. Like, for example, for VM, you have to have, did you want, or you described, okay, sorry. Yeah, microphone. I'll just quickly say, for VM, you also need to have libcap-devel to be able to run some of the tests in like 32-bit glibc libraries, at least headers. So
yeah, I mean, the different, so I was the one who did the patch to take BPF out of the default. The difference of the BPF dependencies compared to most of the other things was that it's not just you need to install a library, which you could probably get from your distro. It was you need a bleeding edge version of Clang and maybe some other bits. So it was hard to even, or not, it was a lot of work to satisfy the dependencies, and it was a very, very moving target. Whereas for most of the rest of K-self-test, yes, you need to go and work out what libraries to install. We should do a better job of documenting that. But it's something you can probably just install from your distro, and it's reasonably tractable.
I agree, though. I would say, I think if you generalize the problem to what capabilities does this test case need? I think it's a general thing. I agree. I mean, BPF is special. Like, you need literally the latest hash of the master branch of LLVM for certain features. You need like the latest PA hole. It's not the same as something like I need a 32-bit header for doing some VM thing. But it would be nice if you could say, for this test case, I need this capability, for that one I don't, and have some.
So have you checked the check dependency script yet?
No, I have not.
Yeah, go ahead, and that's exactly what it does.
Okay.
Check depth script under K-self-test directory. I wrote it because I was struggling with the same things.
Okay.
So if you were to give the architecture, and it'll analyze your test system. It'll run on your test system and say, these are the libraries that are missing, and you have to load them to be able to run full K-self-test fully.
That would be interesting. I think it would still be nice to be able to encode that in the test configuration so that you can have CI systems and stuff use it too. But
so it could be added to run to K-self-test run itself, but I haven't done that. I left it out because I didn't want to include it in the K-self. So check that out and see what it can do for you, and if there is anything that you want to add to that, just send me patches.
Okay, yeah, that sounds good.
And you can also specify a specific architecture, and it'll tell you if you were to cross-compile, it will also tell you what is needed for a cross-compile environment.
Sounds good. I want to talk a little bit more about config later, but for now, I want to take a step back and ask what other, in general, what else should K-self-test be able to do? Like, so for example, for RCU torture, Paul's script, which I know is separate and we're going to port it, but Paul's script builds the kernels that you need in various configurations. It runs RCU torture modules with certain numbers of CPUs and RAM configurations and stuff like that. I think RCU torture, and this actually might be the next slide. Yeah, so this one, Sorry, I was planning on this taking less time. For me, I found that it's quite challenging often to run, to like iterate with K-self-test because I think a lot of people as well are doing most of their testing on VMs. So for me, I compile the kernel. I have to make sure that the config options from the K-self-test suite are there. You boot into the VM with the mounted volume shared from the hosts, and then you run the K-self-test after you've installed them. So some of these, in general, the point that I guess I really want to discuss is that I think a lot of these features, BPF has multiple architecture support, and they have a way of specifying which test cases work on S390X, which ones work on x86. Do we want to go into some of these subsystems and pull these features out into a common part of K-self-test? So that's something like kernel CI or Patchwork, which is what BPF uses, can really use this, as we were talking about in the last presentation, right? Like you as somebody that isn't an expert in this subsystem should be able to just onboard it onto your CI system, hopefully without knowing what it's doing, right? You as a developer, tell me what I need to do to run your test suite. It seems like, in general, maybe pulling some of that out and making it a common K-self-test feature would be warranted. I don't know if anybody else feels that way.
A couple of things. I don't know if I fully understand what some of the K-self-tests do have different architecture support, right?
So
breakpoints would be one example.
So the K-self-tests, sorry, I forget where this is, but you can only specify a single config file, right?
I see.
So
you're talking about just the config file part.
Yeah, so like obviously config x86-64 is mutually exclusive with config ARM64. So, but that support is built into some of the self-test suites, right? I know it is for BPF. It might be for VM it is as well, because I know that they skip certain test cases if they don't have enough RAM or if they're running on an architecture that doesn't have like 5-level page tables or something like that. So, I guess in general, like what I've observed from K-self-test is that it's great in that it's aggregated all of these disparate test suites into a common format for output. A common format for packaging, and do we want to take it a step further and say, this is also a common format for configuration, it's a common format for running across any config or any architecture, and also we'll help you run it in a VM and we'll build it for you locally, so it can kind of function more like KUnit in that regard as well.
Absolutely. Configuration has always been a little bit weak. One of the other things I would say is, in addition to configuration, the other things to look at is when you're testing a particular syscall, for example, system call, and it depends on the features enabled as well, and the flags. So one of the things that that K-self-test, when we thought about the framework, one of the things we thought about is because you won't be able to, even configuration is easier to manage in some ways. So you can say the feature is supported or not, and then it always does a skip and it tells you why it's skipping. So that part, that's a bug if it's not. If a test is not doing that, it's a bug. So other things is that features is the harder part, because features, you still need to be able to run, even if a configuration option is not supported, or configuration option is not enabled, or feature is not supported. That's the whole idea. So we can definitely, configuration part needs, it's a coupled though. Even if you build the K-self-test with that configuration option enabled, you have to have the kernels supporting it. So there's two parts to it, right?
You have to have the what supporting it, I'm sorry?
Kernel enabling that option.
Okay, like a sysctl enabled or something like that.
Well, I mean, any configuration option. It could be, any random configuration option, or even a kernel having a particular, based on the revision, if 6.0 implements a new flag on a system call, that might not be available on 5.19. So the test still needs to run without modifications. It should be able to run on older kernels.
Wouldn't it be nice if the maintainer that wrote the test cases was advertising to you what was capable, just in like the way that like K-self-test forces you to express what this test case can do and what it requires as part of like how it's configured, instead of having a config file where you basically have to have all or nothing for the test suite to work.
Well, hey, it's in the kernel tree for that reason, that we can make changes the way we want. So developers and users also. So yeah, I mean, why
All
not?
right, that's why we have LPC. Everybody can get on the same page.
I suspect there may be a philosophical question here that's worth tackling head on, which is some users of K-self-test may want to have a single config, and then they can run all of the tests across multiple configs, multiple subsystems in one go. A subsystem developer might want a unique config to test their subsystem, which may be mutually exclusive with other subsystems. Or in the case of RCU torture, have a series of configs that they want just for that one subsystem. And that is at tension with the people who want to comprehensively run lots of subsystems with a single standardized config. I suspect those two will always be in tension, and you'll have some compromise between the two, but like, that's the reality, right?
Yes. So the reality is, K-self-test I have done these presentations before, what K-test intended to be. It's a developer test suite primarily, so developers write tests and be able to run. That's why if you notice, we will support a bunch of different options. Being able to just go into the test directory and run that, just run tests in that directory, like here. And so, yes, there is going to be push and pull between what users want from it, what developers want from it. So we weighted more towards ease of use of developers. We are moving it towards users, but they sometimes those are at odds. They can be at odds. Having said that, though, I do see the need to improve the config part of it. We have individual tests supported, and then they do the right thing, but yes, we can.
Well, thank you very much.
Thank you very much, Dave. Next, we have Alexander to talk about Syslog. I believe, or Dimitri, or both.
Are you going to be here? Are you going to be here?
Oh, so remote. Oh.
Okay, next one, there's a remote. There's a remote.
See if we can show the video on the big screens. Do you know how that works?
The one that was
Do I need to do it from here?
Shepherding this. And if there's any issues, I think I have to run back with the AV guy just to check it over, make sure everything's in. Mike, I think is coming too, just in case, but Kate had.
Okay, we can see you in the room now here.
Yes, so we want to make sure, I'll start helping too, but you're going to be the shepherd?
Alexander, can you hear us?
Yes, and can you hear me?
Right. Yes, we can hear you. It's all ready for you to go now.
And are you able to see the presentation, or do I need to press some start button, or how does it work?
Excellent presentation. Give us a second. You have.
I guess.
Yeah, perfect.
I think it's fine like this. Yeah, we can see you in small and the slides in big. Okay.
Yeah, so we can start. Okay, so hello everyone. I'm Alexander Nekich. I'm member of the Kernel Dynamic Tools team at Google. And today I will talk about our efforts to make Sysbot reports more developer friendly. We'll briefly talk about the Sysbot itself, about how it attempts to facilitate bug fixing, about important changes over last year, and about our future plans. If we have time at the end, I'd be happy to hear about the difficulties you face and maybe your suggestions on what should be further improved. So Sysbot is a continuous kernel fuzzing system. First, it checks out and builds kernels from multiple trees with multiple configurations. Then it fuzzes them using syscaller. Then over time, it collects and sends bug reports. And finally, tracks the reported issues. If you've been involved in Linux kernel development, you must have seen some of our emails, quite a lot of them. First, sysbot reports were sent in 2017, and since then we report between 1,000 and 1,500 bug reports per year. We try our best to avoid false positives, so we don't send everything that we detected. As you can see on the slide, the gray columns that detect issues are much bigger than the brown ones, the reported issues. We intentionally skip and ignore crashes that are likely to be of little value. Also, as you can see, at least according to our counting, quite a number of reported issues unfortunately remain unfixed. On the left side, you can see the distribution of bug types we report. Most of them are either warnings or KSM reports. Bug type is one of the very important factors why some bugs get more attention than others. On the right side, you can see that for the reported KSM bugs, almost 50% are fixed or are resolved in 100 days. For deadlocks, it's already around 40, and for info reports, it's only 30%. So what can sysbot do to increase the share of the fixed bugs? So sysbot tries to generate a stable reproducer for each bug it finds. Firstly, for each newly detected bug, it attempts to craft a sys reproducer in syscaller domain-specific language. Such a reproducer is interpreted in the same environment in which the bug was originally triggered. You can see an example of such a program at the bottom of the slide. If a sysrepro is successfully generated, sysbot attempts to isolate the reproducer even further, down to a standalone C file. Currently, we are able to find a C reproducer for 53% of the bugs we report and 6% more on the FSC's repro. According to our data, the existence of a reproducer greatly increases the chances of the bug becoming fixed. In 100 days after reporting, bugs with reproducers are resolved 1.5 times more often, as you can see on the right half of the slide. If a bug has a reproducer, sysbot can also remove the burden of setting up the environment and running the reproducer manually. The user just needs to send a reply to the bug's email thread with the systest command and specify the kernel tree to check out in the patch to apply, either as plain text or as an attachment. You can see a simple example of such a command on this slide. It asks the bot to check out the Linux tree to apply the specified patch on top of that and run the reproducer there. And after processing, sysbot will reply with either a success message, like one on the screen, or with a failure report. All the execution logs will be attached to the bot's reply. And according to our data, last year we received and served around 1,000 patch testing requests from Linux kernel mailing lists. If you're dealing with sysbot reports and never used the patch testing feature, give it a try. It should be pretty convenient. As a logical continuation of reproducer generation and patch testing, sysbot also performs fix and cause bisections. This is unfortunately a tricky process, so it's not enabled on all our sysbot instances and does not always succeed. But when it succeeds, it also increases the chances of the bug becoming fixed. So as you can see on the right side of the slide, the bug has a reproducer. About 55% of the reported bugs are resolved in 100 days. If there is also a cause bisection, then it's already 65%. Let's look at what changed during the last year. For each reported bug, we have begun to share kernel build artifacts. That is the bootable disk image on which the bug was triggered and the corresponding kernel object file with the debug info. The disk image can be downloaded and run either on JCE, like Sysbot does, or on QEMU. And also on this slide, you can see the part of our report that contains such links. The other important change is related to automatic bug observation. The problem is that we're not always able to figure out whether a bug has already been fixed. Some bugs are fixed independently from being reported by Sysbot. Some bugs are fixed without letting Sysbot know. And as a result, we kept quite a number of no longer relevant bugs on our web dashboard. Bugs without the reproducers were automatically closed after no crashes have been happening in a while. Now a similar approach is applied to bugs with reproducers. If existing reproducers are periodically retested on the latest kernel commit, and once no working reproducers are left, the bug is closed. In 2 weeks, more than 60 bugs have already been obsoleted this way, and there's more to come. The next change is related to strace. Strace explicitly dumps syscall arguments and return values, so its output should help better understand what exactly led to the crash event. If a reproducer is found, syscaller runs it once more under strace, and if it has led to the same bug, syscaller captures and shares the output. You can find that in our emails on the console plus strace line, like demonstrated on the screen. And one more change is related to perf subsystem fuzzing. Sysbot had managed to find an easy way to trigger lots of RCU stalls and task hangs. It liked the perf event open call so much that it was present in almost every corpus program. And it caused lots of benign stalls and even sneaked into lots of non-relevant reproducers. And now it's no longer the case. We're still fuzzing the subsystem, but on a separate instance and with much stricter rules for bug reporting. And now let's talk about the features we're planning to release in the near future. We've been receiving complaints about two problems. First, it's difficult to find all Sysbot bugs related to the specific kernel subsystem. One could only do a text search on the web dashboard page. And secondly, bugs reported to LKML, unfortunately, can get lost over time. So the plan is to implement and deploy an explicit bug into subsystem classification. On the web dashboard, there will appear per subsystem list of bugs, and we're also planning to send aggregated lists of still happening issues to individual kernel mailing lists. And now the question is whether we're actually able to do such a classification reliably. Here you can see the current approach that's taken by Sysbot to detect guilty files. We follow the stack trace and skip frames based on a set of rules. For example, we skip all library calls because bugs are usually in their callers. We skip sanitizer source code functions and so on and so forth. The lists are actually quite big. The first non-skipped frame is said to be the guilty one, and then we just take the file where that code stays. On this slide, you can see that we skipped all list management functions, skipped generic device handling code, and we got to the HCI reduce to def call. And it actually turns out that even such a simple approach is quite reliable by itself. Here you can see a simple experiment. For already fixed bugs, we already know their original crash reports and we know their fixing commits. So for reports, we can run the previous algorithm, and we can also take the commits themselves. After feeding that data into getMaintainer.pl script, it turns out we can already guess at least one mailing list of the fixing commit in about 75% of cases. So not too bad for such a simple approach. And we're now trying to further improve on that. To help debug issues for which there is no reproducers, we plan to collect and share kernel core dumps. Together with the VM Linux file, which is already shared, this can hopefully improve the current situation. And we also received complaints about reproducers for file system bugs. So we plan to provide not only reproducers, but also raw faulty file system images that were mounted by those reproducers. Hopefully this will make the life of file system developers easier. So thank you very much for your attention. If there is anything that was not mentioned and that could improve your own experience of dealing with our reports, please let us know, either right at the conference or you could also send us an email to our mailing group. Yeah.
Thank you. We have 5 minutes left for any questions. Any questions in the room, maybe?
I really like that feature of being able to download.
Okay, so I really like that feature of being able to download the image. So that'll help a lot of people. I'm currently mentoring about 19 mentees that look at SysBot bugs, and that would make their lives so much easier. And then also S-Trace running, I do that all the time. That's a great suggestion for that I'll share with my mentees, to have them run S-Trace, SysBot reproducer under S-Trace. So thank you so much. So drop an email when you have the support for image extraction or downloadable image ready, so I can go play with that.
We already shared the downloadable image, and it's not yet getting public. It's not getting reported for 100% of our reports, but it will soon be.
Okay,
so
thank you.
You can already see such emails.
Okay.
Oh, thank you.
Is the output now in KTAP format, or is that a possibility if it's not?
Could you please repeat the question?
So is the output of your reproducers, what's the format of that? Is it in the same, is it in KTAP output or?
So there are 2 types of reproducers, one in an internal DSL and one just C. And those reproducers are meant to crash your kernel. So you take the config and your kernel just goes. And then you can attach with a debugger or whatever. So it's not really, doesn't really have an output except for crash, I think, right?
Yes, when we report a bug, we do share the kernel configuration on which the bug was triggered, and we do share the program that crashes the kernel that was built with such a configuration.
Yeah, I was going to say the most useful output of the SysBot reproducer is the kernel stack trace. Right? That's not KTAP.
Yeah, like the whole architecture of syscaller is that we make the kernel crash deliberately on every time the kernel looks weird. We even crash on panic. We even panic on warning. I mean, yeah, that's kind of the whole deal.
We have a couple of minutes left. Any more questions? Okay, well, thank you very much, Alexander. And
thank you very much for your attention.
Yeah, great. Next, we have Dimitri to talk about fuzzability. I guess, is Dimitri online as well? Okay.
I warned him that he needs to. I told him. Okay, he's ready.
Hello. Hello, Dimitri. We can hear you here. Can you hear us?
Yes, I can hear you, but I don't have an option to upload my presentation.
There's a plus button in the bottom left. Does that work if you click on it? And bottom left and take presenter.
There's no such button for me.
Okay.
But you need to be able to switch them, so just let it go. So take it and give it. Any presenter can moderate, you can give it. Oh, so take it and give it.
Okay, I just saw it for 1 second and then it disappeared again.
I made him presenter, someone else undid it. Let me just go do it, make him a presenter right now.
Okay, I see it again. 1 second, nope, it disappeared again. It appeared for a few seconds and disappeared.
It's interesting. Let me take presenter and then I'm going to load your slide up for you and then give it to you. See if we can get it. Sure, I'm not seeing that presentation uploaded. Is it there?
Everybody can load it when he has it.
Oh, okay. Just a second. Let me see if I can give it back to him being presenter then.
Okay, I see the button. Mhm.
Okay. Go into manage your sessions and upload it.
I'm trying to upload. Okay, cool. Can you see the slides?
Yes.
Okay, great. So let's go. Hello, my name is Dmitry Vyukov, and I'm going to talk about how to design subsystems for fuzzability. And so we work on kernel fuzzing, kernel fuzzer syscaller. And this talk is reflections on why some subsystems were easier to fuzz and we get better coverage, while some other subsystems were harder to fuzz. I will answer questions at the end, and we also have a syscaller matrix chat room that will be active for the next 3 days. You can ask questions also there and about my talk and about Alexander's talk as well. And I will mostly skip the intro slides because Alexander already did intro in the previous talk. So Sysbot has a dashboard at syscallerupspot.com. There you can see a list of the open bugs we have. And for each bug, you can see lots of information about this bug. And also one of the things we have is coverage reports, which you can also find on the dashboard. And if you click on it, you will see an HTML where on the left side, you will see kernel directory structure and files with % of coverage. And if you click on the file, you will see actual coverage for this file. And this usually very useful to figure out where the fuzzer has stuck and why it's not making progress. So we have some subsystems that are better covered and some subsystems that are worse covered. And this talk is basically about how to make your code well covered. So there is significant overlap between fuzzability and general testability. And I would define testability for the kernel roughly as you can write a user space test for it, This test can run in a virtual machine. This test is isolated and reproducible. It's fully automated, and you can test all features in a single kernel build. But fuzzability adds some additional aspects on top. First of all, the code needs to be hardened against crazy inputs. This generally is true for non-root subsystems, but it's not always true for root-only subsystems. Also, it needs to be isolated and reproducible in presence of random inputs, and in particular, don't require some special tricky setup and tear down sequence because the fuzzer may just not do this sequence. And it should be reasonably easy to generate inputs automatically because they are generated by a program which is not as smart as humans. Okay, now I will move to some concrete aspects, and the first one is elephant in the room, which is requiring hardware to test a subsystem. So usually we have some hardware and then a driver that talks to this hardware, and then we maybe have some common code for this subsystem and a test that talks to this common part. So the claim is if your subsystem requires particular hardware, then it will not be tested and it will have bugs. Even if it was correct initially, people will do refactoring. They will try to fix some minor bugs and introduce major bugs and so on. So in solution to this is what's called stubs or emulators. And the most famous example is probably a network tune device. So it pretends to be a network card and allows to test the common part of the networking stack. And also the test can inject network packets from user space. So for this reason, it's important for the test to be able to talk to the stub. There are other examples as well. And in this case, we don't test the actual driver code, which is suboptimal, but say if you look at the common part of the networking stack or media or USB, the common part is very substantial. So it's totally worth testing on its own. So another thing you can do is you can create an emulator for actual hardware, and this way you can activate the driver code as well. So this is better because we get more coverage. But the thing is that I think there's currently no good way to actually write such tests. So there is KUnit platform mock that is supposed to do this, but I think it's still not quite there, and there are not lots of good examples that you can look at to write your own stuff. And for completeness, you can also create a stub in QEMU. But this is unfortunately not working well for us. One reason is that in this case, test cannot talk to the stub because it's actually outside of the kernel of the machine. Also, lots of testing today runs in the cloud, and you cannot supply your QEMU for the cloud. You can of course run QEMU in a cloud virtual machine as nested, but it usually turns out to be very slow and barely usable. There are also issues with isolation and reproducibility because QEMU usually creates one or few global devices that became shared, and they're always in a dirty state. Also, for completeness, you can actually run syscaller on your actual hardware and fuzz your driver this way. It's just we are not doing this on sysbot, but you can do this locally. Okay, even if there is a stub, like some of them are still not very well suited for us. For example, a stub may allow creation of only one or small fixed number of devices, and then those became shared and in dirty state again. Some stubs allow to create new transient devices, but then they become sticky and require some special cleanup to destroy them, and the fuzzer just not doing this cleanup. So they again become shared and global and dirty. Some only work in init namespace, and some require very complex configuration, which fuzzer has hard time doing. So what would be the ideal situation? Ideally, I would like to see something like you have an ioctl on, say, your debugfs file, which creates a completely new fresh stub. Maybe it accepts some initial configuration for the stub, and it gives you two file descriptors, one for the stub part, and then the second one for the actual device part that user space can use to communicate with this device. And since those are file descriptors, they will be destroyed when the test process terminates, and they will be automatically cleaned up as well. So that's how an ideal stub would look like. Now we're done with hardware and move to some general recommendations for just normal kernel code. So again, it's always good to have fresh transient instances for whatever your subsystem provides. And memfd create is a good example of a good API versus, let's say, shared memory IDs or IPC IDs, which are global shared and thus frequently in a dirty state. Also, don't do unreasonable restrictive assumptions, like say only initnet or only one instance of your resource. Also provide killability, which is like ability to kill the process with kill -9, which is generally true, but we found at least one case, which is Fuse, which creates processes that you cannot kill -9, which is very nasty for fuzzing. Also, sometimes we see some global settings, for example, sysctls that allow you to switch between, say, configuration A and B, for example, doing BPF-JIT or not doing BPF-JIT. And this is not very handy. It would be like better if user space could ask for JIT or not JIT with every program, say, load this program and JIT it or not JIT it. There still could be a global setting that would restrict possible option, but it's still like would better if the test could ask for a particular configuration. As I mentioned, code should be hardened against crazy inputs, even if it's root-only code. First of all, it will allow to test the non-crazy part, which you do want to do. And second, just think about, say, bugs in user space program run by root. Maybe it's been just developed. For example, you developed an admin tool, and like as you developed it, it just crashes the kernel because you have some stupid bug. In some cases, we have to disable some subsystems in testing because they just crash all the time, and developers say that it's not an issue. Warn on. So do use warn on to for various invariants and assumptions in your code. That's what will allow fuzzer to catch logical bugs in your code besides just crashes. And we actually found lots and lots of them, so they are very useful. Also, they're very good for documentation, and documentation that you actually can trust and that is up to date as compared to, say, comments. If you have some expensive checks that you don't want to enable in production build, you can add a separate debug config that will enable those checks. And please, please, please don't use warn on for any kind of bad user inputs or bad hardware behavior. Use it for, so warn on should mean kernel bug. Only that will enable automated kernel testing and fuzzing. And now we move to the last part, which is design of UAPI. So Syscaller based on descriptions of UAPI in a special DSL language called Syslang. And this language contains descriptions of system calls with their argument types, also descriptions of enumerations and structures. So you can roughly think of this as C header file declarations of function enums and structures. And this is what allows the scholar to generate some more or less reasonable test cases. But this also, the consequences that you cannot, yes, and the distinction with header files is that it has more semantic information and it's completely machine usable. So there are no implicit parts and comments and so on. But the consequence is that it cannot describe just any crazy interface. It can only describe the things it can describe. So the general recommendation is stick to standard patterns because the language can describe all of the standard common things. And I will show you some examples of non-standard things that we discovered. As you know, in most cases, collections are passed to kernel as arrays. So you have pointer to element and number of elements in the array, right? But we found one case, I think, where a linked list is used to pass the collection to the kernel with the actual next pointer in the structure. And this created some issues for the fuzzer because like initially it went into infinite recursion and there were some other issues. But also it created issues for the kernel because this actually structure needs to be converted for compat handling. And as you can imagine, converting a linked list is very non-trivial. So it required some significant amount on complex code to do this. And as you can guess, it also led to some very bad security issues because the user space can actually modify that memory as you try to convert it forth and back. And that becomes very tricky to handle because you cannot say first count number of elements and then convert it because the user space can actually change things underneath. So the next example is use of user space pointers as IDs. And we found, I think, 2 cases so far. And one is in the old asynchronous IO subsystem. So you can issue an IO request. And if later you want to cancel it, you need to pass exactly the same user space pointer to this function, to IO cancel function. And this pointer will be used to identify the request you want to cancel. And for this, we still don't have proper support. So the fuzzer just usually doesn't pass the same pointer because it's not used anywhere else. And again, as a recurrent pattern, this also created an issue for the kernel itself because it cannot blindly trust the pointer passed. It needs to verify that it's correct. And to do this, it works a linked list and a global mutex, which is just disaster for performance. There is an actual comment saying this sucks. So if this code would use a standard pattern, say FD or IDR, then there also would be standard function to handle this efficiently. Yeah, consistency. So there is a thing called network device ID, device index, and everywhere it's encoded as in32, but there's one place in the kernel that uses uint16 to pass this index. And this is very nasty for the fuzzer because it knows about things like, say, file descriptor or device index, but this notion is tied to the underlying type, which is, for example, it knows that file descriptor is always in32. So we actually cannot describe this, the same thing, but in a different type. We can say it's an device index, but then it will be 32 bits and layout of the structure will be masked. Or we can say it's just a random integer. Yeah, this is one of the cases where that kind of makes you want to find the developer and ask why. Net filter. So long story short, for net filter, you need to pass some large blob of information from user space in a super complex format, which includes some parallel arrays, some cross references, some derived info, array size of arrays with variable size elements, which is almost always like a pointless thing to pass, and some other things. So this format was just a nightmare for the fuzzer to generate like correct instance that will pass some initial validation. And as you can guess, it also lead to dozens and dozens of bugs in the kernel in this conversion and check-in code. And I think they're still coming. Next thing is human-oriented Chatsy protocols. So when you want to create a new pseudo terminal, you want to obtain 2 file descriptors to both ends of the terminal. And to do this, you open a file. It gives you a handle to one end. Then you need to call an ioctal which gives you an integer, and then you need to convert this integer to a string to form a file system path. And then you open this path, and this gives you a handle to the second file descriptor. And this sequence is like harder than necessary, and it's harder for the fuzzer to kind of create, and especially this conversion of integer to string, because it doesn't appear basically anywhere else. So we don't have good support for this. So again, how an ideal interface would look like, it may be, say, pipe-like interface where we have single ioctl that gives you file descriptors to both ends of the terminal at the same time. So the summary for UAPI, basically stick to existing patterns, be consistent with existing code, don't use convoluted formats with derived info, be nice to machines. At some point, we hopefully will do automatic extractions of those interfaces and some inference, but this will require interfaces to be consistent even more. And it's always a good idea if you develop a new subsystem to also write syscaller descriptions at the same time. So this way you get some early fuzzing coverage, but also it will make you use better UAPI patterns just because you won't be able to express something that is not standard. Okay, and the recap for the whole talk, basically allow testing and virtual machines, provide fresh transient instances, use warn on, and stick to standard UAPI patterns. And with this, I'm ready to answer questions if we have any time. And as I mentioned, we have Syscaller chat room. So if you have any remaining questions, feel free to ask them there. Thank you.
The room's mic was muted, and so you may not be hearing it. I think technically needs to mute the mic in the room, the on-site room. People asking questions. You don't need to unmute yourself, Dimitri. There was an echo happening earlier.
Any questions?
I'm looking, see if I find them there. If people have any questions, if they could type in the chat while we get the sound sorted. Good. The room is unmuted and need to be unmuted. So for the AV text in the room, if they could please unmute the mic, that would be helpful. Still got the room muted. If people have questions, could they type them in the chat in the interim so we can relay them on to the speaker? Sorry, Dimitri. Multiple things going wrong simultaneously here.
Okay, that's
so fine. To get this figured out.
Hi.
Ah, hi.
Can you hear me?
I'm in well. Yep, we can.
Yes.
Go ahead and ask your question.
Okay. How to first thanks Dimitri's contribution, and we are trying to build our fuzzer against our drivers. And one challenge of us is that in the iApto syscalls, and we need a better way to generate the patterns automatically. And currently we just scan our code and to capture that the comment argument that we pass to our iApto calls, and that argument will fall into some switch case. But I just want to know, is there any better ways to generate that
I
numbers?
almost get most of the questions, but not some of the details because audio quality is not good. So what exactly is the issue with the ioctal argument?
It's I just want to know if there is a better way to generate test patterns.
Better way than what? I don't know. Maybe that's a better discussion for a chat, that metrics chat or mailing list, because I feel it
Okay.
will need some like details.
Okay, thank you.
Yes, feel free to use the metrics chat or the mailing list. Sorry.
Okay.
Yeah, the room is live again, so that's why the sound is coming in and echoing.
Yeah, I think we have the 20-minute break now. So thank you, Dimitri.
Yeah, thank you. Bye bye.
Thank you.
Thanks.
Hi, Philip, you're already a presenter?
Yes, hi. Hello, hey, can you hear me?
Yes, we can hear you.
Yeah, okay, I already the present. Okay, okay, start. Thanks for attending the session. Yeah, this is Philip.
Hear you in the room.
Okay, so can I start?
Hello everyone, we're just about to start again with Philip Lee in 1 minute online. Philip, can you hear us?
Yes, yes, I can hear.
This is your slide here. So are you all set?
Okay.
You have
Yes,
control
I
to
can.
switch the
Yes, I
slide?
can. Yes, I
Perfect.
can try it.
I think you can start. Maybe a few people will come later, but you're fine to start now.
Okay, sure. Yeah, thanks all for attending the session. This is Philip from Intel, who is the maintainer of zero-day CI test service, aka the kernel test robot. What we observed is that this kernel community has evolved the testing to cover each important test activity in a modernized manner, from developing the testing to service to result consolidation, bug scrub to release criteria discussion. So all this largely formalize the testing effort, connect different pieces together. Today, I will talk about the status of such trend and how each part works together, then the involvement from zero-day CI perspective, after which we want to exchange the ideas and have discussion around any enhancement or missing part of this virtual team. Community-wide testing is decentralized and independent. No doubt, with the collective effort, more capabilities are added, like the bisection now becomes the standard part of most CI. The shift-left testing can detect issues in earlier stage, and the coverage-based fuzzing exposes a lot of issues. We can think of more of such examples. More players enter this field to provide a valuable perspective to contribute to the larger-scale testing. So the question in my mind when I observe this, what are the key events to finally result in a full functional QA team? This is a simplified loop to describe the workflow. It is a very high level and conceptually right. The flow is already there from the beginning, while the way we use it to participate in this daily and the mindset we have keeps evolving. The accumulated changes leads to big difference. So let me expand further. Usually, the analysis of requirement is important to have the right tests planned and implemented. Meanwhile, in a few areas, the advancement in test methodology decouples such needs. One highlight is the adoption of test auto-generation, like the Trinity and syscaller test syscall in a fuzzing way. The kernel builder testing utilizes random configure to do massive testing to find corner cases. Then in each testing level, the adoption of engineering, like from the unit test to integration to more complex system level. This best practice is the way how developers can test their own code in first place. And the new ideas keeps coming, like the road test for driver regression testing, like the static analysis running by a total robot. They all extend the landscape of testing. In test execution phase, to maximize the output of test suites, continuous running is a must, either by individuals or by a test service. More players are contributing to the coverage of Linux kernel, especially different robots. It is not easy for any developer to duplicate the full CI in developer's own side. There's different model to connect with CI. The typical case is like kernel CI, which allows distributed testing from any place with a central place for results. And because of the enlargement of test scope and the pursuit of in-time results, so there's a need to have more grown computing resource and storage. So this results in most test services, if not all, are hosted in cloud for better scaling. Next, it comes to test report and the bug scrub. Here, the bisection is quite helpful to provide hint when there's many changes mixed together. There are commonalities across different testing efforts, like the need to report out the finding and how to measure the quality. I like the idea of KCIDP to consolidate the results and allow customization of user to subscribe what is interested. Usually, maintainers and developers trace into reported issues. It could be helpful to have a general way to trace important problems from the whole kernel's view. With the debut of regression board, it connects different pieces, like the bug spread in Bugzilla email discussion and the CI report. The difference it brings, I see, is it streamlines this activity that make it more than a single tool, but a kind of a maintainer on the regression side. And the collaboration with developer becomes tighter. Tools like LKP tests, TuxMake, the repro script from Syscola are designed for developers to easily reproduce the issue and verify the fix. And there are discussions focuses on the release process, and some are already discussed in early session, like how the release criteria are and how to implement this. So these are all important to assist maintainers to decide whether everything is ready to send the pull request or whether it's the right time to accept a pull request. Now, to have a summary for what have been talked so far, every test activity or typical practice is now having corresponding ownership and modernize the methodology. Of course, the newly introduced ideas are not replacement to existing approaches, but more like they are as a whole, and they are different pieces to solve a puzzle. That's why I say for functional virtual QA team emerges. And the ZDCI is glad to be part of this journey. It is the very first service to provide the full stack coverage on all repos and the mailing list. Also, it adds bisection as its native capability at the beginning. It focuses on build testing a lot by utilizing random configure and the shift left testing. Later, it brought static analysis, promoted a more strict warning check, adopted CLAN, and recently adding the KSMET tool. The reason to increase the build quality is to achieve a higher success rate of runtime bisection. Otherwise, the bisectability cannot be promised. ZDCI is partially open sourced with LKP tests tool, which integrates more than 80 test suites from industry, which tries to provide a uniform way to run them to analyze the result. The other part is kernel build and the test service, which is running in Intel internally. We have some focuses recently. First is we are investigating how build issues can still be escaped to mainline after all the shift left testing effort, what we can further improve. Secondly, ZDCI is bisection driven. We only report out the issue if bisection is succeeded. This means when some bisection fail, the branch can contain issues that we haven't reported. So hopefully we can analyze the failure pattern to learn something, to learn some general findings and feedback the learning to the bisection logic. Machine learning also has the possibility to assist the testing. We are adopting this in log analysis to judge the bisected commit is related to problem or not before human is involved. Also, we are prototyping to reduce the test scope based on what is changed to do more focused coverage. Last but not least, we look for wider collaboration, such as joining KCIDP to post what we have tested. And this is still in the playground phase. Later, we will migrate to the production. Any discussion, and we also have some discussion like any practical approach to open source small pieces of 3D CI. And there are a lot of discussions regarding improving the overall testing in community and this is just one more. I will share some challenges opens from the general experience and open for discussion after that. For the code change, the developer is doing the necessary testing at the first place. While there's a limitation sometimes for how widely the test can be, considering certain change may have higher risk or wide impact. Here, the shift-left testing could be helpful to engage early if developers post to mailing list or their own repos. The next part is how developers can communicate what tests are already there to cover the changed code. So the test service can acquire such information to provide feedback in a short time. Or this can expose the test coverage status to maintainer, also to gather the test quality. Systematic test coverage would be hard if considering the available platform and different test focus and resource. The diagram is the rough data how the CI runtime coverage is, and we regularly review this to try to fill the gap. So hopefully gradually more test suites or test strategies can be introduced. And the next change is the smooth test execution is relied heavily on existing test suites. Any behavior change of test cases, either the test result or the output format, would impact the automation side. So test compatibility is kind of important. A related question is whether same test suite version is applicable to mainline, to stable, to next. So only one binary is needed to maintain and run for all repos. There are a lot of things we can optimize, like the bisection, like how to select a smaller test scope, and also the test duplication. For example, we do a lot of random config testing, but some config seems to have no effect. Probably it's an indicator that most or some of the random config are duplicated. That's why some is not effective. Oops, I seems skip one page. Yeah, now let me get back. Yeah, this is for shift-left discussion. The purpose is to reduce the funding on mainline, so we can test a lot of coverage from developer side. I think there are two parts. First is how the CI can engage early, so maybe developer can subscribe to the CI service. And also for the patch testing posted on mailing list, developer can have some responsibility like to specify the base, so it's easier for robot to have had a chance to cover it. Besides that, developer could have their own way to validate the code. Such method may not be covered by existing test suites, so it's helpful to move them to well-known test framework. This can allow such test ideas be run regularly by any test service. Next, any problem can be solved by AI, by machine learning. Is there any practices that we can learn from? Based on the current reported by tech, we can see usually the top 10 covers about only half of the findings. So this is kind of the pattern of long tail. The rest are found by a lot of individuals. How can test service further help here? The rule in kernel is we don't introduce regression. While it is possible, some real problems are only detected at a later time, such as some corner cases. Would it be a requirement to fix all the regressions? The trace of regression is another challenge. Well, with the support of Bugzilla and the regression bot, it is under better control now. We are interested to have more capability to understand the kernel quality. For instances, with some kind of data mining, we can answer the queries like what is the most risky component, so we can look for more test cases for it. Is the coverage enough for this submitted code? Whether the test result is false positive if we do a cross-check on another test service. Now, in the last stage, a clear description for developer to reproduce is very helpful, though there's still chances. Some issues are quite dependent on the environment. And what to do to ease the maintainers' work. Here is one example. The maintainer describes the acceptance criteria and obtains the answer in a one-click way by querying a test service or querying KCLDB. Here, the criteria can be like there's no build failure, what self-test pass, the changed code has 50% coverage by K-unit tests. So this can assist the maintainer to do the judgment more easily. That's all the challenges I listed. I try to avoid duplication to early discussions. So if you have any comments, inputs to these challenges, or anything you want to discuss, yeah, feel free to share. Yeah, thank you.
So one of the things I'll observe is that very oftentimes upstream developers are constrained by just available resources. So they're, speaking just as the ext4 developer, the standard 4K block size default, I try to make sure is failure-free all the time. However, occasionally there will be flaky failures that only happen 5% of the time, 10% of the time, and QA departments like Louise, they'll want to run tests 100 times, right? It's the same test suite 100 times. A test suite takes 2 hours, so if you're going to run a test that takes the test suite that runs 2 hours, 100 times, that's 200 hours. That is not something I have time to do, so I don't do it. And so therefore, there will always be some flaky test failures or some esoteric configs where, at least in file system land, there will always be failures. I wish that were not true, but I don't have the resources to apply to that. Now, a virtual QA organization sounds great, except for the fact that it usually requires very specialized knowledge in that subsystem, because very often the reason why those flakes are still there is the senior developers have tried for an hour or two to try to fix it, got nowhere, and said, I have better things to do with my time. So if you take a relative kernel newbie and ask them to try to fix a bug which very clearly is a flaky bug that only happens 5% of the time, that's not a recipe for success. Right? And so this may be unique in the file system world just because file systems are highly parallelized, store a lot of state, and are prematurely optimized to within an inch of their lives because people care about performance above all else, right? Which are the three things that you should never do if you want a robust program, right? Don't premature optimize, try to avoid storing state, and try to avoid threads if you can all help it. And file system violates all of these principles. So, very often the file system people are talking about all of these hard problems we have, and I'll be the first to acknowledge this may not be as true in other parts of the kernel. But I suspect if you poke hard, you will find that there are a lot of flaky tests. The tests are dependent on the nature of the CPU or storage device that you're using. A whole bunch of things that make this a very, very hard problem. And that doesn't mean that we shouldn't try to solve the low-hanging fruit, right? But I think we do need to acknowledge that sometimes, some of the corner cases, which are the ones that I think those of us who are kernel developers care the most about, are the really, really hard ones, right? An easier thing to do is to run tests on the LTS kernels and discover commits that need to be backported to the LTS kernels. And maybe that's a good way to get people who are interested in testing but who aren't deep experts, being able to contribute in some way. And so maybe that's another thing we need to think about is, yes, we have a lot of resources. How can we get them to learn how to do the deeper stuff and not run away in frustration when we give them really, really hard bugs?
Thank you very much. We're kind of running out of time for this one. Well, if you have a quick question, and then we have another talk.
So I've worked at Red Hat for a number of years. We've had similar problems. And is there a way to instrument XFS tests or instrument a system to collect debug data? Years ago, we had a problem with NFS. Same problem, you run it 100 times, it's really flaky. We decided, we're just going to do a Wireshark dump of the protocol every time we run the test. And every time, if it passes, we just throw it away. If it fails, then we just give it to the NFS team and say, hey, look, here's a Wireshark dump. And they just parse through the data. And after a while, they started noticing trends across this flaky data. Now, it took months because it flaked maybe every 100, 200 times. But after a while, they collect enough data, like, oh, there's some trends, here's some problems. Okay, we finally found the problem. Is it? Yeah, so I'd like to take some time and encourage fixing the flaky tests in XFS.
Thanks a lot, and thanks, Philip. Next, we have Brandon, I believe, about key units, and David in the room.
Yeah, I'm actually loading that's okay. And then I'm giving you.
You should be able to take that.
Okay, cool. All right.
All right. So yeah, we're going to be talking about KUnit. Most of this talk is going to be a discussion about the long-awaited function redirection. Our third attempt at it, I think. But also, we're gonna go over some of the stuff we've been doing over the last. I'm sorry, I just want to set it. Yeah, whatever. We'll also be going over some of the stuff we did over the past year, but we'll try to go over that stuff really quick. Also,
yeah, this is function redirection or doubling down on KUnit, as we can't go without a pun. So we'll quickly go over what's happened with KUnit. As we mentioned, function redirection proposals, tooling features.
yeah. So, yeah, like you said, new tooling features. We'll go on a little bit on more of that later. We also fixed, finally have support for testing init sections, which was something that was asked for several years ago, and you can do that now. We also no longer conflict with module init and shutdown init functions for modules. Jeremy Kerr actually added that. I haven't seen him here, but if he's watching, thank you. That was a pain. We also, not really KUnit, but we got KSAN support working on UML, which given that we really like UML, even that's an unpopular opinion, that's very, very helpful. Google coworker Patricia did that work, but it was finally carried over the goal line with some nasty bugs by Vincent Whitechurch. We've seen a lot of growth in K-unit. We're at 500 tests now. We've been seeing super linear growth for the past 3 releases, so that's pretty exciting. A pretty substantial portion of the, I don't want to say total, we got a lot of tests from the DRM subsystem. They're going to be presenting actually really after us, and we'll talk more about that. We also saw a pretty substantial amount of tests from Chrome OS. Now, going into some of the new features that I think are kind of cool. We have this, we have a new kconfig add, which allows you to add individual configs right from the command line, which is really, really helpful for being able to send like one-liners over IRC. We also have this keyunit config option, where we had that before, but you can chain them now. So you can actually use that to merge
easier to understand. But for the main thing we want to talk about is function redirection. And this has been a problem basically since the beginning of KUnit. There have been several attempts to implement mocking or stubbing or something like that, because unit testing is really, really good if what you're testing is like a pure function or some other really isolated unit. But as soon as you have, calls out into the rest of the kernel, which happens a lot, or you have global state, hardware state, basically there's so much global state everywhere in the kernel, global lists of devices, etc. It starts to fall apart. The traditional solution is you have mock versions of things. This all works reasonably well outside a totally written in C kernel, which has no access to any pleasant language features. And the only way of dealing with that's huge numbers of macros. So every attempt we've done to this has been really tricky. And indeed, we've got a link to a whole web page of attempts of doing this and why they're unpleasant. Ultimately, though, we can simplify a lot of these cases down to you want to call a function, and instead of that function executing, you end up with something else. And there's plenty of ways of doing that in the kernel. None of them enormously suited to testing exactly off the bat. So what we've implemented now is a new API, and indeed we've got a couple of different backend implementations for it that basically lets you take a function and redirect any calls to that function from within your test to another similar looking function. And the first implementation of this is really simple. We call it static stubbing, and you basically just add this macro to the start of your function, which compiles down to if KUnit's disabled, nothing, and if KUnit is enabled, to basically a check, is the test running? Has this test redirected this function? If so, call this function and return instead. You can activate it, change what it's being done with a simple KUnit activate static stub function. Because it's basically just a function call, it works on every architecture under the sun, has no dependencies. The downside is it's a little bit ugly to put this macro at the front of every function you might want to call, particularly since you're probably going to want to stub out a lot of functions when you have a complicated test, some of which might be pretty important system functions. If you have really good eyesight, you can see an example of this being used here. Basically, the first function to add one has this macro at the start saying, redirect, and you just pass the function name and then all of the arguments. And then we can replace it in the test by just activate static stub, replace add one with subtract one. And when we want, we can deactivate it again and go back to using the normal implementation. The way this works is that redirection only happens from within the K thread that is spawned to run that test. So if you need to replace a function that's critically important to the kernel, there's some protection around it not causing your entire system to crash immediately. Though, again, this is the reason why you shouldn't run KUnit tests on a production system. The other implementation we have, which provides an almost identical API, is based on ftrace. This, has slightly different performance characteristics. The API is the same. The big advantage is you don't have to put that very ugly initial macro in at the start of your function that basically compiles down to the call. It also, by default, has no performance overhead, though there are ways around that for the static stuff that may happen with being able to use a static call. The downside is it requires ftrace, which is not available on every architecture, and it requires more than just basic ftrace, some of the live patch features. There's another code example. It's basically exactly the same as the previous code example, but missing that one line. You also can't run ftrace-based stubs on inline functions because if it's inlined, you can't exactly intercept it in one place. So we have this macro kunit stubbable, which just compiles down to no inline if kunit's enabled and nothing if kunit isn't. So our questions for you all are, is this as useful as we think it is? How terrified are you at the prospect of one of your functions suddenly being pulled out underneath you as a kernel developer within a test? It'd be terribly scary to do this with, kalloc and the like, but, there are a lot of important functions people want to mock out. Is disabling inlining a more terrifying prospect, or is adding these function redirect macros a more terrifying prospect? All of these are free if you don't have kunit defined, but with people building production kernels with kunit enabled, even if they're not running tests, just to have the same kernel image, there might be some performance thing there. And, several other questions, can we optimize this? Is Kent's code tagging feature an interesting way of implementing some of this? For the ftrace-based implementation, can we support more architectures? Over to you all.
Hi, are you able to inject errors using the ftrace or some of these stubbing mechanisms?
So you can use this exact API. You could inject an error by replacing the function with a function that just returns the error. It's not, a single one-line inject an error on this thing, but once you've got that function, you can just replace it quite easily. So yes, but it's a bit more broad in scope than that.
Yeah, one of the things I like about kunit is it's getting harder and harder to test the error path as you get closer to the hardware, right?
Yeah.
So it just seemed like this is a simpler or an easier way for developers to kind of get engaged or test these paths.
That's the hope. Ben.
So I guess from my perspective, given that a lot of the code I work on is architecture independent, ftrace seems fine. And I would never enable it in production code, so I don't have any problems with it. Other people may have different opinions. My big question is, I want it now. When can we get this upstream?
So there's an RFC out there, and V2 of it went out a couple of days ago when I realized V1 didn't compile anymore. But it's been out there for a little while. The biggest issue with ftrace architecture support at the moment is that it wasn't working on UML, which is our default for kunit, and is much faster. But there's no reason, if people are really interested, they couldn't port ftrace to UML. Patches are welcome.
Thank you very much. We're running out of time for this talk, but it's been great. Yeah,
Thank you, everyone.
We have another kunit talk by, yes, I think it's you. Maybe not. Sorry, is it your talk next?
Yes.
Okay, sorry, I think the name has changed on the schedule.
Yeah, it was Theo, I guess.
Oh, okay. So not the speaker on the schedule, but isn't it? I think sure I will upload the slides for you.
Okay.
Put it full screen here. Also, it's here. Yeah, okay. Yeah, otherwise we'll do it.
The title is?
Yep.
Okay. Thanks. So, hello, I'm here to talk about how to introduce KUnit to physical device drivers. I'm Thales Aparecida. I have a bachelor in computer science from Unicamp, Brazil. And as you may know, I'm here to talk about result of multiple Google Summer of Code projects under the XORG Foundation umbrella, developed by me, together with Maíra Canal, Magali Lemes, Isabela Basso, and mentored by Rodrigo Siqueira from MD, and Melissa Wen and André Almeida from Igalia. The goal of our projects was to basically learn how to write unit tests for physical device drivers using the MD display driver as a subject. The MD has a huge code base supporting multiple generations of their GPUs, and it's under the variant subsystem. Our initial expectations was to have a lot of problem mocking GPUs, but also worrying how to write unit tests in a way that the community could contribute more, and keeping ourselves aligned to the MD guidelines. So we started the summer converting the DRM self-testing KUnit tests, which actually started as a hackathon in Brazil. And those tests that were converted are currently part of the DRM official suite of tests, which are also integrated in the IGT GPU tools. And our development first started to learn how to use KUnit as completely beginners in the kernel. We picked some functions that were clearly independent from the GPU. And then we picked some tests, some more tests, and this time picking tests that were clearly dependent of some specific generation of AMD GPUs. But in the end, in both cases, of course, in this case, we still didn't have any problem mocking GPUs. And finally, trying to force ourselves to find some code that actually depended on GPUs, we started to look in the mailing list to find regressions so we could write some KUnit tests for them. And again, we didn't need to mock any GPU interacting code. So to kind of look the footprint we left behind, we managed to run GCOV, which is currently a great potential project for future GSOCs, because it's currently only supported by GCC 6, but it just confirmed our findings thus far. There is a lot of code in the MD display driver is actually completely GPU agnostic. So there's a lot of low-hanging fruit for our beginners in the kernel development. Beginners who are interested to contribute to the kernel to write unit tests with KUnit without any knowledge about GPUs. And the thing that I came here to discuss was that actually there's a lot of functions that are static that might require tests. And it's really tricky to reach every code path without actually testing the static functions. And KUnit has support for writing tests for static functions, but if you don't agree we should test static functions, we could of course expose them as global. And as they said, you can either write a separate testing module with KUnit or write the test inside the driver module. So just to brush around the code, you could write KUnit tests for the driver, injecting the KUnit test inside the driver code by just including it in the footer of your test code. This last approach is documented in the kernel documentation. Otherwise, if you don't agree to write unit tests for static functions, you can, of course, expose them in the header file, include them in your test. For the other approach, you can write a test suite module. But of course, to write a test module, you would need to export your symbols. So in the case of MD code base, most of the functions are not exported. So you will need either to export them conditionally, but like David said, some people are thinking about enabling KUnit in production. So I guess this can impose some memory problems. And which we learned, we can actually export the test case itself. So if you don't want to export or like add noise to your functions, you can export the test case inside your module and write a test suite with your, including the test cases. And finally, if you have nothing against writing tests for static functions, you can combine the two approaches. You can inject your test cases, exporting the test case inside your driver code, and include them in a separate test suite. So just before we start discussing, I would like to thank the XOR Foundation for accepting our proposals for the Google Summer of Code. Thank my mentors from MD and Igalia. Special thanks for MD for donating the GPUs that we thought we would need to run the test cases, but in the end, I guess they were needed to at least run their own code. And a special thanks for the Linux Foundation, not only for this event, but also for sponsoring my trip here, without which I wouldn't be attending in person. Thanks also, Shua, for the ticket for the event. And you can also watch my teammates, Maíra Canal, Magali Lemes, and Isabella Basso. They will be presenting at XDC later in October. So now for the discussion, what do you guys and girls think about writing unit tests for static functions? Anyone has, or just to bind them, do you have any thoughts about writing tests for as tested modules, or to write tests inside the driver itself? Maybe depending on your pipeline, you have some thoughts on that. And maybe for DRM people present here, would you have other topics to talk about? Like we converted the DRM test from K-self-test, which were integrated in the IGT to KUnit. So would you like to keep them running inside IGT, or would you like to run them as KUnit in your pipeline? So yeah.
It depends on two things.
Okay.
I think it's. I don't know.
The other one.
I don't think one of them does.
This one.
This will work. One or two things. So static functions, I think it's a good idea to write them. Not a problem. The conversion that happened going from K-self-test to KUnit would be, it's good to have that probably, but it depends on if users can run it. Meaning, does that continue to work as a regression test? So I would make sure that it does, continues to do that. Of
course.
And it kind of keep going back and forth. Driver tests inside, you sometimes do need tests inside I have done it in the past. You would, as I write the driver, I would have a test code in the driver that could be invoked from either user, not just a driver, any module, kernel module, you could have that. Reliably, you have to have a way to test that, meaning be able to, however you do it, either you do this, a couple of things to think about it is, do you include the test code in the production code, or would that be something governed by another configurable? We do have that in the kernel. We do have a lot of test and debug options that we compile in, and then also sometimes we load test modules to test. So I am, in general, going back to what Ted said too, I am going to question I wouldn't personally include any test code in production system, on production systems. That would make me very nervous. Because for one thing, you're not testing the test code as much as the actual code. So I would kind of question the sanity, but that's mine. Looks like you have something to say?
On unit tests for static functions, I think everyone agrees it would be really nice to be able to test static functions. As you go through all of the different ways of testing them, it's a bit awkward. One thing we have thought about is conditionally exporting, as you say, individual symbols. So, having a define KUnit exportable or something, or exported for testing, which is static when KUnit is disabled and not when it isn't. And one possibility there is there's symbol namespacing. So if we can export symbols in a separate symbol namespace just for testing, that hopefully will perhaps not eliminate the problem, which I think most people are most scared about with exporting internal functions, which is namespace pollution. That's a way of ameliorating that a bit. So that's one thought we had, but certainly personally I sit firmly on the side of, maybe not every static function needs its own test, but the vast majority of them probably could benefit from it. Yeah. And, as mentioned, tests inside a driver's module itself versus having a standalone test module. I come down on having it in a standalone test module is best if we can do it. And the problems, the reasons to have the test inside the driver module are all basically, it's awkward to put it in a separate module. We don't have the ideal technical solution for that, not philosophically, this is where it should be.
If I'm not mistaken, the ORM actually has a macro for exporting for tests.
Yeah, I think that's the right way to go about it. And maybe symbol namespacing is a future path to walk down to make that more palatable to more people.
Yeah, and just to mention the manual of the regression tests that we wrote were actually for a static function. So there is clearly need for some testing there.
Yeah, definitely namespacing. And what happens if that, you have to be careful about ABI, for sure. And standalone, like modules, isolating, remember I was touching on isolating the test code. If it's a module, it is easier to isolate and load and unload. You can just take that out as opposed to making it part of the driver module.
Yeah.
So as long as you can do that easily, dynamic runtime, that's what module will give you, the ability to load, run your test, unload.
Yeah.
So that is really good to isolate that way.
Yeah.
Yeah, I think the to-do item probably for KUnit on this is part of the argument between standalone test modules versus having tests inside driver modules is that the only way we have to trigger running a test in KUnit is loading that module, because tests run on load. And if we had another way of triggering a test that was not so tied to module load, much of the argument about which of this is better would disappear.
Yeah, one of the things that my team didn't know. Okay, one of the things that my team didn't know was how were people using KUnit. So which pipelines were using KUnit and how were they running, either by the KUnit tool or by, I don't know, some other starting point. And that would help to make it clear how to write the code. So depending on the pipeline, if the driver module has something special that it has to be loaded and then the test should run. Like, I don't know, I'm not sure if the platform test would have something like that.
Yeah, I'm obviously also very interested in how people are running KUnit. I think our goal certainly is it's best if tests work no matter how they're run. So if it's possible to implement things in a way that is not dependent on running it using KUnit tool or using some other, using modules versus built-in, the best tests are ones that run in any environment.
Yeah. Any other questions or commenters?
Just a simple question. So all your KUnit tests you did for the AMD DRM area, how many bugs did you find?
How many bugs?
Or uncover?
We didn't actually find bugs in the test we initially that we chose to write, but we try to write tests for regressions currently being worked on the main list. And actually, one of the regressions that we worked, the initial value, because the story of this regression was initially the code was not compiling for 32-bit architectures. Then there was a commit to fix this, which added the regression. The function started resulting in 0. So there were some fixes in the main list which made the value stop being 0, but actually started returning completely different values from the start. So I don't know if that is a bug, because I'm not sure that this proposal was not upstreamed yet. So I'm not sure how the function will be in the end. But
I just want to know if you had any payoff. You did all this work, like 10% of the DRM code you showed up there. Was there any payoff? That's all I was trying to get to. That's usually the excitement. You write all this KUnit stuff. You're like, okay, did I find something, prevent something, do something I was just curious if there's a payoff.
Yeah, that was the closest we got from find something. Like the one proposal in the main list was resulting in a value that is probably not correct. But I guess that is kind of a bug we found.
We'll take the small win.
Yeah, so far.
Well, I think that if you took self-tests that were present before and you moved them into KUnit ones, they would keep passing. It's not like you try to add additional tests, right?
Yeah. This conversion from K-self-test to KUnit was actually a part of a hackathon to teach some people from the university how to write KUnit tests. So I guess it just was easier to look at some tests that were already done before writing the tests.
Just to add to that a little bit, one thing that we did notice is KUnit's tooling has made it a bit easier to pick up some interesting things like code which only works on some architectures. So there was a DRM test for some function, for some format conversion, and the test originally only worked on little endian architectures. Having KUnit's tooling around meant we could easily just run it with arch equals PowerPC and notice, oh, this test fails now, it must be endianness dependent, which it was. So.
Okay, so I would just like to say that beginners, KUnit is very easy to learn, and don't be afraid from device drivers, because there's a lot of low-hanging fruit there. Thanks.
Thank you.
Thank you very much. Next talk is Jan, and that's the last talk for the session today. About that grid. I think.
I don't have the presentation. You uploaded it? I don't see it.
That's like very late talk.
Oh, yeah. Okay. Okay, I'm gonna upload it for you.
It's on.
Okay, thanks.
I uploaded it in the break, so yeah. So I'm Jan Lübbe, I'm from Pengotronics, and we do embedded stuff on ARM. So that's a little bit different background, I think, than most of us here. So the perspective is perhaps a bit different. So I'm going to talk about LabGrid first to give you a bit of a background, and then talk about what I'm trying to do with integration with Kernel CI. And then I have some description of what I did as an example, and we can have a discussion. So LabGrid is a hardware control framework or lab control framework. So you have many boards and racks and ARM-based systems. You have serial console networking, GPIOs, USB, whatever. And you want to control them from your development PC or from automated testing, maybe in GitLab or something like that. And we also want to have low-level bootstrapping capability because when you let developers work with these devices, they tend to break the bootloader or something like that. And so we need to be able to automatically recover them to get them back to a defined state. Otherwise, automated tests make no sense if you don't know your baseline. So LabGrid has basically 3 layers. We have resources, which just describe which hardware is connected to the device and how to access them, so like a serial console in this case. And then we have drivers written in Python, which talk to these resources and give a high-level API where you can use Python code to control them. In this case, send characters, receive characters, and you can layer those drivers to build more useful interface, for example, which know how to talk to a Linux shell or bootloader shell. So you don't need to repeat that in your test cases. And then these high-level drivers implement protocols, or you could call them APIs, which are standardized across some classes of drivers. So both bootloaders and shells know how to execute commands and return the output. And if you have lots of diverse devices in your labs, you need to configure these drivers somehow because they need to know, for example, what prompt to match and so on. And we do this configuration in YAML. So you can define resources explicitly, or I come later to that over the network. And then you have drivers which have configuration like what is the prompt, which username or password do I need to log in. That basically encapsulates all the information I need to know to let a test suite run against a given device. So in most cases, I don't have all this hardware connected directly to my machine where I'm logged in or in the CI client. So I have some set of clients. Those connect to a LabGrid coordinator, which knows which resources exist in my lab. And those resources are exported by exporters. So an exporter has, for example, devices which implement a power protocol or console protocol, digital output, so GPIOs, or Bootstrap. For example, the NXP chips have a protocol via USB where I can upload the bootloader, the Rockchip SoCs have something similar, but it's all vendor dependent. So, and in this case, in our lab, we have like 150 boards by now, and they grouped into places. So all these interfaces that are connected to the boards are grouped into places. So we can take a board out, reuse a place for something different. And so they get names in the exporter. And the targets are connected to these interfaces on the exporter. So with that in the background, I can write test cases in simple Python with LabGrid as a library and execute commands, interpret the results, and have basic regression tests on systems which basically run the software that is actually also shipped on those devices. So we are not using any test runners on the devices itself, they're just remotely controlled. So the abstraction level we have in these tests is usually what I want to, what I would tell a colleague to do if they want to use a manual test. So I tell them, run HW clock, wait a bit, take a look at the result, and either the test is okay or not. So for Kernel CI, our goal with this is basically the remaining issues we see in the field is not so much in the generic code, because we have lots of very nice testing frameworks. We have the 0 day, we have Syscaller and so on, which find most of the hardware independent bugs before we see them. So we basically want to do something similar for diverse hardware and run those on real hardware without mocking. So what's missing there is basically the set of brand new kernels built by Kernel CI. They built from many many maintainer branches, they build next. So every day I get dozens of new kernels with new interesting changes that I want to test on the real hardware. So I need to basically go to Kernel CI, find the interesting kernels, download them, run them on my hardware, and maybe feedback the results. And it's also an interesting incentive for our customers to get normal dev config working on their board, because that enables all this work. So yeah, it should help get them to the level where they run mainline kernels on their boards, because then they can benefit from automatic regression testing. So basically, the workflow I want to do is filter kernel CI builds that are interesting to that hardware, download those kernels, init.rmfs and so on, device trees, deploy them on the device with the existing interfaces via USB, via network, whatever is actually supported by that hardware, and then compare the results with some mainline known baseline that works well. So for example, I did a test with a BeagleBone. It's got connected to one of our exporters. So it's just connected via USB for power and Android fastboot, so to upload the kernel, and has a serial console. And on the other side, it has an uplink via network, which also powers the whole setup. So again, I have a YAML configuration, which tells LabGrid how to control that board and how to move it into different states. So basically how to install a kernel and boot to shell. So I can automate that with a generic test suite to run basically the same tests on many boards. Yeah, so in my simple test case, I run, in this case, the LBatch pipe latency. And interestingly, it seems that the performance has increased, so latency has decreased between 5.4 to 60 RC something. So that's something I need to look at, but if it is true, that would be nice. But yeah, that was simply a result of the test run I did. Yeah, of course, I have open questions, otherwise I wouldn't be here. So is kernel CI interested in results like this maybe from boards that are not mainline? So should they just be submitted and under which names?
Yeah, that's a very good question. The issue with submitting results for boards that are not available to the public is if someone sees the results, that something is failing, only you would be able to fix it, for example. So it's not very useful in that sense, or it's a bit misleading, or it's complicating things. So, however, it's possible to have to submit the results like a project we've been working on with Nikolai is KCIDB, which is a bigger superset database where we can send any type of result if you want. So that way, at least, it wouldn't be advertised in the same way as the native kernel CI stuff. But it would still be useful to know that on some platforms, some tests are failing, because then if you provide the logs, maybe people can see why it's failing, and maybe some other platform somewhere that you don't know about will be able to reproduce the issue. So I think that's probably a good way to deal with it.
I think it would be nice to be able to see correlation between changes in performance or in functionality, even if the platform is not in mainline.
I'm not sure the unobtainable platforms are a real issue. I mean, like, I know I've got boards in my lab that you can't get anymore because they're old and they're out of production. And there's things you can order, you can actually order, but they cost an arm and a leg, and nobody's going to order them. And blah blah blah. I don't see the
obtainability as being an issue.
I mean, yeah, one of the reasons, one of the issues is, for example, if you do an automated bisection and you send a report to someone saying your commit broke this platform that nobody else can access, then it's a bit awkward for the person who receives the bug report. That's a kind of issue.
Sure, but I mean, that's going to happen. That's going to happen anyway. You know, people just, not everybody has every piece of hardware. To me, to me as a kernel maintainer, I don't really care if I could actually go out and buy this Intel laptop that somebody's broken the audio for or not, because I'm not spending £1,000 on a laptop because of some kernel bug. Go away. And the fact that, you know, whether, and if it's a point somebody won't sell me, that's not really materially different to me.
Yeah, that's completely true. At least it's possible. The other one is not turned on. At least it's possible to find a platform somewhere, like, you know, sharing or asking someone to submit a new test with the patch. But I mean, yeah, that's one of the things, I suppose. I mean, if it's real, like, confidential hardware, maybe you won't even be able to share the logs. I don't know. So
yeah, so basically the summary is it would be useful in KCIDB, but probably not in the existing kernels.
Okay, so what I'm hearing is, yeah, you want to report to kernel CI. Really, what the goal is to get maintainers' attention, correct? So one thing, you can report it through kernel CI, or you could report it if you were to run these tests, say on the stable releases. Don't know if you're doing that, so you could report it there. Say for example, the performance test that you talked about right there, you are seeing performance improvement, great. But what if it becomes regression? So in regression, regression lists is another place. Lower has regression lists. So you could, if you saw any regressions, you could report it there. Really, the goal I'm guessing here is for you, by looking to put it at report result to kernel CI, is really getting community's attention to the problems you're seeing.
Yeah, I think that's one part, and with something like Tux build, I think we could also easily automate the bisection locally. So if we know how exactly the kernel CI kernels are built and can reproduce that exactly, that would be very useful. So yeah, on a performance change like this, it should be pretty easy to run a bisection test.
I have a question for you. Do you have some logic already in place for detecting when there's, do you have some logic in place already for automatically detecting when there's a performance regression? No. You just look at the results by hand, yeah.
So this is the result of a few days of hacking. So it basically adapts the kernel CI API to get the kernels and just 200 lines of Python to talk to LabGrid and run the tests on local boards. But it's, yeah, at that level, it's a proof of concept.
So if you'd be interested in submitting those results to KCIDB, you would need to find out how the builds you're using are identified in KCIDB, and I think Guillaume can help with that. And then you just generate some JSON and send it off through a pipe to a command. And that's basically it. Like, you just need to refer to those builds in the files they just send in, and these will join the results in KCIDB.
Yeah, I know the object IDs in kernel CI, so...
I don't know if they're exactly that in KCIDB, but they are should be pretty close.
Yeah, are there other use cases, features where something like this might be useful? So basically, yeah, automating running kernel CI kernels on custom hardware on a lab.
Well, I'm kind of more interested, sorry, I'm not going to answer your question. I'm kind of more interested in the protocol that you used to get the kernels from, and the kernel related artifacts from kernel CI, and if we could possibly standardize that on that across the industry.
I think you probably doesn't want that because that's the old API.
Oh, is it? Oh, okay. Well,
Actually,
you know,
it is getting standardized with a new API. You get an event when there's a new build, for example. You get an event when anything gets sent to the database, for example.
well, it's not the events as much as like the JSON. I mean, are there like, have you guys talked to TuxMake to see if like the metadata that you put in your JSON is the same for kernel CI as it is for TuxMake, or?
I did look at the data initially that they had. I think it doesn't really matter if it's not exactly the same as long as it's possible to machine read it and it has all the information inside that's needed. I think there's going to be some design differences between TuxMake and the new API that means it's difficult to have exactly the same thing coming from the API. But we could easily have a bridge in between, something that receives events and submits events again with the format that's like for the same as TuxMake, if that.
Okay, so let me do my big ask. Can you upstream that to like the kernel make files, the creation of the metadata?
Well, it's not really, well, maybe. I think there's a few steps I think we have to go through before we get there. But yeah.
Thanks for all of you to help with that.
I'm willing to help. It's not my API.
Yeah, but KCIDB gets built both from Tux Suite and kernel CI. So in principle, we can work on plugging in there and, you know, caching both of those.
Any one of you wants to look at that with YouTube tutorials?
I just wanted to ask a simpler question. That picture you showed of the device under test and the controllers, what's the controller made of? So, yeah, is that a custom board that you've? Do you have have you got an open design for that, or a BOM, or is there some way to reproduce those boards? Because the problem we often have with a lot of lab systems like this is someone does a one-off design and then we can't buy them again ever. You know, the parts go out and no one keeps them going. So.
The Linux automation people have talked about this previous conference. Those should be available in the shop.
Cool, thanks.
Okay, thanks. Thank you very much. Now we've run out of time again, so thank you very much, everybody, for your questions and everything. And we can hang around it a bit more if we want to have informal chat around here. I think the room is not going to get closed now, but video streaming will stop. Thank you very much. Have a good evening. Might see you at the party tonight.